Today we're going to talk about, this talk was, I started it because I had heard that Joe Horn was going to talk about random numbers. And I figured, well, let me do more the empirical side of random numbers. But here I am, I'm thrown under the bus.
And Joe deserted us.
Yes. When you deal with random number generations, and here I'm talking about uniformly distributed random numbers between 0 and 1, 1 is excluded. Let's see, hold on a second. Okay. Computers favor algorithms that are that work with integers and generate random numbers as the last step. So whatever they do, they work with integers, they fiddle with bits and all that. It's all integer operations. And the last step, they divide a random integer by a big integer and give you the random numbers. This allows portability to work between across implementations, operating systems and all that. So portability is good. Calculators use random number generators based on floating point. And right there you are at the mercy at the floating point rounding system. And so two HP calculators that use the same floating point arithmetic and rounding will reasonably give you the same random sequence of random number generation. But if the rounding is different, then you get a different sequence. So when you're using floating points, portability is kind of shaky. Calculator games and simulations require generally less random numbers than computer games and simulation. Now, the high count of random numbers generated in computer graphics and simulation dictate very good PRNG algorithms to avoid side effects like beginning to recycle or bad distribution. On the other hand, the low number of random numbers you use in calculators, games and simulations, turn out to be very forgiving because you're not going to generate enough random numbers to see the bad effect. So that's kind of the good news.
I have a question.
Yes.
What is the P in PRNG?
Pseudo-random number generator.
Okay,
because
thanks.
they're
Yeah.
not really random.
Okay.
I did a study and went over, I started my study and went over a large number of them with some legacy random numbers. You'll recognize equation 1, 3, and 5 as equations you've seen in stat packs that HP made or keynotes or maybe PPC, those three. This one, this is an old version. It's not in Doda. I double checked. I found it somewhere, I can't remember. And of course, equation number 5 is the PPC random number generator. I started a couple of years ago and I did a study. Of course, there was the die-hard test. And you had to submit a file with 1 million random numbers, and it gave you all kind of statistics that were weird. The results were confusing. So I decided to do my own stuff. And I decided that I'm going to generate random numbers, obtain statistics to these, and then create a penalty factor that tells me how bad the random numbers are. So here, in this study, I'm going to present a third generation to calculate the penalty factor. The first generation defined the basic test for batches of 100,000 random numbers. And of course, the tests were not as extensive as the die-hard, but it was a starting point. Then after a while, I thought, well, maybe I need to add some more tests. So I had the penalty factor calculated based on 1 million random numbers. That was a good leap forward. And I added some more tests, and I created batches of 1,000 batches. So each algorithm had a billion random number generated, divided in 1,000 batches, and then I would calculate the statistics that I want. I would calculate the average and standard deviation of the penalty factor based on these. The third generation, I decided that among the tests, and I will explain, that the autocorrelation lags were too small. It ranged from 1 to 100. And I figured if I have 1 million random numbers, I should do it from 1 to 1,000. And of course, that added calculations I was using, and I was MATLAB that had the stuff built in, and I noticed that the time it took was longer. So I decided that instead of using batches of 1,000 runs, that I cut them down to 100, so that the calculations stay within reason. For example, when I ran generation 2, I had at least 2 machines running round the clock, and the stuff ran for weeks. And when I was done with the second generation, I had generated 1 trillion random numbers for the stuff that I did, for the stuff that I tested and wasn't good. Each generation of these approaches calculate at the end the mean and standard deviation. And I always start with a random number given to me by the software so that I don't have biases, and go from there. The penalty factor is based on the following set of statistics. The mean value of the random number generated, its standard deviation, and then I look at the maximum and minimum autocorrelation taken from 1 to 1,000 lags. The maximum is a positive number, the minimum is a negative number. The first and second generations only went from 1 to 100 lags. And I figured for 1 million random numbers, I could stretch at the cost of additional calculation time.
Namir, what's the lag?
Like you compare, say, the neighboring elements, or maybe 2 elements down, or the first. Say a 10 lag is from the first and the 11th element, to see if you jump by every 10, if there's a correlation. So you start by comparing immediate neighbors, but then you begin to compare further and further neighbors. You're jumping further and further. If you see there's a hidden pattern that overall will
reveal some
yeah,
periodicity.
it's going to cycle. Yes. And then I also did chi-square statistics based on 10-bin histograms, and each bin is 0.1 in width, and of course between 0 and 1, and the statistic was, I called it chi-square 10, and the expected value in each bin is equal to the number of random numbers I generated divided by 10. And then I decided to do a chi-square 20, where I kind of doubled the resolution. The bin width is 0.05, I have 20. Perhaps the next generation, if I do that, I will use more bins. Of course, that will mean more computational time. I also look at some of the products of the autocorrelation values times their count. And these autocorrelations are distributed into 20 equally sized bins ranging from the minimum to the maximum. So the ranges depends on what I get from the autocorrelation. It's not fixed. And then these are, the last two are the most recent statistics that I added. The change of sign statistics, I will talk about that later. And then the Kolmogorov-Smirnov statistics. And these, they compare the distribution of the random numbers with the theoretical distribution. And I have 2 statistics, the K sub plus and K sub minus. So I calculate the penalty factor by basically taking, using a sum of weights times the statistics or functions thereof. So for example here, I take the mean, the absolute of the mean minus its theoretical value, 1/2, and then I add standard deviation minus its theoretical value, and I multiply by 1,000. Why? Because I've noticed even bad random number generation do give you numbers close to this. That's why I added a high penalty. Otherwise, you wouldn't show any effect. Then I take the positive value of the maximum autocorrelation minus the negative value of the minimum autocorrelation. So I'm really, in effect, adding two numbers, multiply by 100 and add. And then I multiply 100 times the autocorrelation sum. And then I add chi-square 10 plus chi-square 20 over half. And then finally, I have 10 times the change of sign statistic plus 10 times k sub plus and k sub minus. Over time, I've noticed that the penalty factor for the first generation, because it was lacking these two, had smaller values. But when I went from generation 2 and 3 and I tweaked some of these weights and all that, I came out with values that were close enough, and that was good. I did use MATLAB to perform the calculation, because MATLAB allowed me to create arrays with 1 million elements. I tried on the HP Prime, it barked at me. And MATLAB also had built-in autocorrelation functions and all that, and of course there's vector math and you know, so the code was a bit more compact, and I relied on the stuff that they had tweaked and fine-tuned. So the calculated penalty factor measures the following: the deviation from the expected basic statistics, the mean and standard deviation, the goodness of the distribution of the random numbers, and the level of autocorrelation, and then the change of sign of the difference between random numbers, and finally the closeness of the cumulative distribution of the random numbers I generate with their theoretical expected value. I'm going to introduce the tables of formulas of, it'll be in like 8 sets. I use variables, the following: R, S, and T to indicate the current and last two random numbers generated. Symbol phi is the Fibonacci constant, which I use a little bit. Log 10 is the common log algorithm. I do use the following set of integer constants. I started with this one, which was in the HP 65 stat pack, and sort of I added 9s here, and then I said, well, this is around 10 to the n close, so I went on the other side and I did 1, 1, 1 and these two. And then I also used the difference between some of the pairs of these constants with similar magnitude. And every now and then I would also shift by pi. So I use an empirical evolutionary approach. I would come out with a set, do testing, and then say, okay, what else can I do, and so on. So I went into 8 sets. What I present here, and the detail is in the PDF file included, is the stuff that made it. I mean, there was more algorithms that bombed out horribly and terribly, and there was no need to consider them. Now, the first set, you will recognize this one, and this one, and as the from the legacy, and includes some of the other stuff that I sort of tinkered with and added new formulas. Set 2 and 3 are simple. The second set, I take the fraction of 1 over pi plus a constant times the current random numbers, and the constant here ranges from 1111.11 to 1111.1111. Set 3 is simply the fraction of a constant times the current random number, and the constants being one of these integers. And these two sets are very small. You can see them here.
Question: in your random numbers, how many digits are being retained by your MATLAB?
I don't know, whatever MATLAB's own precision.
Because the number of digits beyond the decimal point is really critical.
Yeah, of course. Yes. Yeah. And that's the problem is I'm using MATLAB to be able to do this stuff, but because I cannot do these tests on a calculator. That is a little bit of the dilemma. Set 4, I use sort of like a mixed algorithm here. It's the fraction of a constant A times the current random number times a constant B plus B times the last random number. And A and B are these constants here. And I test if R is equal or greater than half, and if it is, I switch the values of A and B. So the whole point in random number generation is to create chaos. Chaos is what you want. So,
But you don't want to do Knuth's algorithm K.
what?
You don't know about algorithm K in Knuth?
No.
Well, he does a random process, a random number of times in a random order, and it ends up the thing ends up locking up and getting it into a single number every time.
I think there was some of digits that did something like that.
Yeah. Knuth's algorithm K is famous from the 1960s.
So, and then there's the other one also. I have pi plus k times r. I'm sorry, the product, that's another group. I do products of r plus s or the exponential of r plus x, and I multiply by these constants. And then the last three algorithms, I do fraction of pi plus k times r, and k is in one of these constants. And you see here the algorithms. Like I said, the PDF has everything detailed. Most of these, you see there's an if statement. The last part is just a bit more straightforward. Set 5, I use the current random number and sometimes the last random number also, and I have similar forms, and sometimes I shift by pi, and I use constants A and B. These are the A's, and the B's are here. And this shows you the list. Set number 6, I use the current and the last random numbers R and S, and I use combination of the square root of R over S and the sum of R and S. And here are the equations. For example, here I'm using the square root of RS. I'm adding pi. So I'm using a different variation on these. Here, for example, I'm using the square root of R over S, but then I multiply by exponential of the sum of the last two random numbers. That's a set number 7. I use the current and last random numbers, respectively, and I use ratios between these constants and R plus pi, R plus 1 over pi, and R plus 1 over R plus pi. Yeah, it's a lot. I mean, that's why it takes days for these. If you imagine you're generating 1 billion random numbers for each algorithm. And the last set, I use the current random number and the last two, respectively, and I multiply them by constants, and I add one or more exponential of plus or minus the values of, I use R, S over 2, and T over 3. The division by 2 and 3 is to kind of slightly minimize their effect because they're older random numbers. This is a partial list. The list in the PDF is very long and very complex. The good news is we are, ta-da, results. These are the mean of the penalty factor, and this is the smallest value, 66, and this is the equation. It uses the current random number. But when you look at the list of the other ones, it uses the current and last random number and sometimes the last two. So including all the random numbers does seem to play a good role in creating a little bit more chaos. Regarding our legacy algorithms, so what happened to those? Actually, this one, which I've seen in the HP65 stat pack, did rather well. And then this one that I found in a book did okay. This one that I've used because it was either in the HP keynote or whatever, did okay. But the PPC, I mean, those are. Now, the good news is that because we generate few random numbers, we're kind of immune for the low quality of stuff. So really, if you want the simplest and optimization between simplicity and goodness of fit, this is your winner. You know, if you want a little bit more, this is the way to go. But if you want just save on bytes, the first formula will do well, surprisingly. For more details, you can check the PDF file included. It has a little bit more details about, especially the set number 8, the formulas. Yes.
So you want a larger factor or smaller factor?
Smaller. It's a penalty factor, so the smaller. It's sort of like the AIC and BIC when you do regression. These are like penalty factors. You want them to be small.
Just a
Yes.
quick remark, many of your multipliers, like the ones with all the ones or the 997
Yeah.
X, many of those, some of those calculation might be speeded up by, instead of doing a multiply, do a shift and add. They can be done, because many of those numbers are of such a nature, they're nice numbers, so they can be done, it could be done by a shift and
I
add.
guess you can do that, yeah. I mean, I think MATLAB you can do. I use MATLAB.
Yeah, well, and that, who cares, you know?
Yeah. So this is good for, again, the integer-based random numbers are more portable, and you know, the floating point, you're at the mercy. And here, really, the study is based on MATLAB's rounding. But again, with the calculators, the level of forgiveness is grand, so we're good. I mean, we're good even going back and using this one. We're really good.
Comparing the numbers there, shown right there, what is the real-world significance of the best one to the worst one? In other words, ranging from 67 to 132.
Oh, it's almost like a logarithmic scale, going from here to here. It's very tough.
No, but on the other chart, where it was a bigger range.
Oh.
If I were to have it generate random numbers and display them to me, would
this
I
is-
see the difference?
Even this one, I would say, is bad. I mean, here. You don't even go beyond 67.5. I mean, it's yeah. I mean, all these are generating.
Not equally.
Yeah,
So
about, yeah.
use a simpler one.
Yeah, I mean, this is not terrible, and
No, but what I'm asking is, between the, go back to the page.
Yeah.
Between the best one and the other page,
oh, okay.
between the best one and the worst one, would a user...
It's
of
not
the
a
cell
linear.
group-
No, it's not a linear worsening. It's almost like an exponential. It has a sense of exponential. Yeah. It's very difficult to, you know, for how to minimize the.
But if I use one equation to generate 100 numbers, and then the other one to generate 100 numbers, and I looked at the results, would I be able to see the difference in quality?
What would you use for the quality? Because way back, I used to use mean and standard deviation, and that doesn't tell you much, because they all come out close, around 0.5 and 0.288, whatever.
If these were picking lottery numbers for winners, who's your neighbor be winning all the time with the bottom? I mean, is it that bad? Is it going to show where you're winning the lottery every week if you're using the bad?
Oh, but how many numbers is he generating? That's the thing.
So if you're only doing 100, as Bob was saying, you probably won't notice much
No,
of a difference between any
100
one.
is very small. I mean, I think
You've got enough sample to see the difference.
That's why, like in the hundreds of thousands of millions, we using calculators, not even close to that. So, like I said, because we generate low numbers, we're okay. You know.
So, but there's no reason not to use that 997 because it's quick, it's easy,
Yeah.
and it's going to be great if you run it all night.
Yeah.
So, you know, if we want a little bit better, I would say this one, yeah. But again, these are, here's the irony, is these are the verdicts based on what MATLAB, but then again, the calculated precisions prime is a little bit different. I was able to, years ago, generate a truly cool random number generator with MATLAB, and I was able to sort of like basically take the random number and multiply it by large values and then truncate, and I was truly getting noise, like floating point operation noise. And when I ported it to Excel, it just fell flat on its face because Excel had a different precision, and I was banking on the sort of junk noise at the end being random, and Excel dealt with the rounding in a different way. So,
Chop them off, throw them away.
yeah, anyway, thank you.